LSU with a minor in geology. He's a senior this year, he's graduating in December.
Thank you. Thank you for having me here. Good afternoon, everyone. The topic I'm doing today is called removal of zinc ions from oil and gas wellbore return fluids. First of all, let me start off with a little bit of the outline of what I'm going to talk today. First, I'll start off with the introductions, which includes the problem statement and the sources of the problem. Next, I'll go into the experimental methods and study that we utilize in this project. Third, will be the experimental results, which eventually will lead to the initial engineering implications. And then after that, I'll talk a little bit about the economic analysis, and finally, the conclusions and some recommendations that we have. First, the problem statement. The platforms in the Gulf of Mexico often encounter zinc-contaminated return fluids during the early productions, essentially from these four different sources: zinc bromide completion fluids, perforation charges, compositional zinc encasing alloys, and finally the various minerals in the formation itself. And due to the high toxicity of zinc concentrations, the United States Environment Protection Agency, or the EPA, has a very strict regulations which only allows 5 parts per million, or ppm, of maximum concentration of zinc to be exist in the wellbore return fluids before it's disposed into the natural water system or the oceans. So this has actually caused a pretty big problem at the platform, because current practice actually requires oil companies to ship tons and gallons of these wellbore return fluids onshore, purify them before it can be disposed into the natural water system. So our goal here is pretty simple. We try to develop a purification system which is capable of removing the zinc ions on the platform itself and then to be discharged overboard. And we believe that this system is going to help us first, it's going to help in reduce the operational costs overall, eliminates unnecessary risks, and also save on the time consuming of shipping tons and gallons of brine solution onshore, with potential recovery for zinc ions in the future completion fluids. So in order to address our problem, we actually started off by initiating with a small-scale purification system in our lab and try to extend the results to the platform. And the diagram right here that all of you see is actually schematics of our experimental setup that we have in our lab. And the method that we utilize in this experiment is called the ion chromatography, or the ions exchange method. And essentially, this study is actually divided into the single column study and the multi-column study. And if you all could look at the single column study first, it's basically a column which is about 300 millimeters in height and about 25 millimeters in diameter. And the column is actually packed with a certain volume of resin particles, which is called DOX21K XLT, and it's passed through with brine solutions, which includes synthetic brine solutions which we made in our lab according to the research paper that we read, and also a few brine solutions that we managed to get from the field itself. And for the multi-column study, the concept is actually the same as the single column study, just that we have 4 columns placed at different heights, and each of the columns is actually packed with a certain amount of volume of resin particles. So what happens is, the brine solution is going to pass through the first column, ions exchange is going to take place, flow through the 4 lines, the second column, third, and fourth. And finally, we will collect the effluent brine solutions over here and send for testing and analysis of zinc concentration. And then some further details of the method that we utilize in this experiment. Like I said before, the method that we utilize here is called the ions exchange method. It's fully driven by gravitational force with a flow rate of 46 mils per minute. And if you can look at the diagram on the left, the yellow or white color right here actually symbolize the resin particles, which is composed of insoluble polymers with a functional group called quaternary amine, which can display high affinity towards zinc and ionic complexes. So what happened here is during the ions exchange process, the zinc chloride complexes from the brine will exchange with the resin particles and are firmly attached to it. So hence ions exchange takes place. So when the brine solution is passed through the resin particles, first high charge molecules will get exchanged first. For example, all the heavy metals, and zinc will be one of them. And second, moderate charge molecules will get exchanged next. For example, sodium, potassium, which may exist in the brine solutions. And finally, the less charged molecules will get exchanged last, for example, the sulfates. And after that, the effluents or brine that we collected at the end of the column will get sent for analysis by using inductive coupled argon spectrometer, which is capable of detecting zinc wavelengths of 213 nanometer. And this is how we tell how much zinc concentration we have in our effluent brine. So with that, this is our experimental study. Like I said before, it's divided into single column study and multi-column study. For the single column study, we actually tested for volume of brine towards the racing ratios of 2:1, 4:1, and 10:1. We also tested for resin zinc's absorption capacity by testing the same resin sample against the new brine samples at a different point of time, up to 7 days. As for the multi-column study, we tested for resin's zinc absorption capacity in the multi-column purification system using the same resin sample against the new brine sample in the 10:1 ratio. And following the series of experimental results that we have, I'll start from a single column study. And this graph right here is actually the effects of residence time. It's a graph of zinc concentration in the brine solutions with a unit of parts per million against contact time in hours. And the reason we did this test is because we want to know how effective it is that the resin particles that we choose react in ions exchange of zinc concentration. So in this experiment, we actually have brine solution purified through a resin bed in the volume ratio of 2:1 for 24 hours and 48 hours of incubation period. And if you could look at the green line right here, it's actually the synthetic brine we have. Initially, it's about 180 ppm, and after 24 hours, it actually drops to around 80 ppm. And then for the next 24 hours, it actually dropped from 80 ppm to around 50 ppm, which is a pretty positive feedback that we get for the first time. And in order to get more accurate data, we actually managed to get 2 field brine samples from the field, and we put it into test. And the field brine sample actually initially starts from around close to 10 ppm, and it shows positive declinations for the first 24 hours. And then for the next 24 hours, it actually drops to below 1 ppm, which is a pretty good result. And this experiment showed that longer incubation period displayed a better removal efficiency of zinc in both synthetic and field brine as compared to the control sample. Next, we have single column study as well for our experimental results. And next we test for effects of cycles of purifications. This is a graph of zinc concentration in brine solutions with a unit of ppm against the cycles of purifications. And the reason we did this test is because we want to know how many cycles it actually takes for the brine solution to reach the EPA requirements after purified through the resin particles. So what we did is we purified synthetic brine again through the resin beds in the volume ratio of 2:1 for 24 hours of incubation period. So as you can see from the graph, it actually started from around 300 ppm, and after 2 cycles within 24 hours, it actually drops close to 5 ppm or below 5 ppm, which is a very positive feedback. And next, single column study. There's a final single column study of the experimental results. We have a capacity test of the resins. This is a graph of zinc concentration in the resin particles in parts per million against the number of equivalent volume of brine solutions. So the reason we test for this is because we want to know how much of zinc ions that the resin particles can hold before reaching its maximum capacity. So in this experiment, we have the synthetic brine purified through the resin beds in a volume ratio of 10 to 1 within at different point of time from 0-hour incubation up to 10 minutes all the way up to 7 days. So as you can see from the graph, initially the resonance particles was capable to reduce zinc below 5 ppm, and then it gradually got saturated and increased because the brine solutions increases. And then towards the end of the graph, the curve of each trial experiments become constant as the resin reaches maximum capacity. So in order to further prove our hypothesis, we actually have we take some resin samples, we put it under an optical microscope and blow it at least 100 times bigger. So as you can see, the most left diagram is the original size of the resin particles at 0-hour incubations. And after 24 hours, it got bigger in diameter or size, about 30% larger as compared to the original. And after another 24 hours, the resin particles got even bigger and about 21% larger than the original size. And if you can see closely right here, some resin particles actually show some cracks at the surface because this is because that it's already taken so much zinc ions and you can't take it anymore and it starts to crack or burst. And next, we have our multi-column study. This is a graph that zinc concentration in resins, again in ppm, against the number of equivalent volume of brine solutions. And the reason we have to test is because we want to see how this multi-column purification system is going to improve the ions exchange efficiency as compared to the single column study. So in this experiment, hypothetically, more zinc in the brine solution should be absorbed in this multi-column purification system since the effluence is continuously purified from columns to columns. So in order to test our hypothesis, we have 140 mils of resin particles equally placed into 4 columns at different heights, and then passed through with a ratio of 1 to 10 of brine, or 1.4 liters of brine solutions, purified through with a 0-hour of incubation. And then after that, the resin particles is collected and sent to our analysis. So from the graph, multi-color purification system can completely remove zinc within about 7 equivalent volume of brine solutions, exceeding the EPA requirement. So in other words, the multi-column purification system can actually remove approximately 90% of the zinc concentration within 10 equivalent volumes of brine solutions as compared to the single column study. So we can conclude that this multi-column purification system has a higher ion exchange efficiency as compared to the single column study. So with that, with all the results that we have from multi-column study and single column study, we actually came out with our proposed purification system. This is actually our design. And the chambers over here is actually very similar to the columns that we have in our lab. It's about 2 meters in height and 0.4 meters in diameter. And what happened is well-operated fluids will come in from the wall over here, go up into the control panel, which acts as a regulator to regulate properties such as pH, temperature, and pressure. And after that, it's going to go up to the dynamic mixer, basically acts as a mixer, mixing all the fluids evenly, and then sending to the first chamber, which is packed with resin particles. Ions exchange is going to take place over here, and then send it back to the second chamber, and all the way up to a series of chambers, depending the volume of the brine solution and the flow rate of the solutions. It can go up to quite a lot of number. And after that, for the last chamber, the well-operated fluid is going to come out through the zinc detector, which acts as a detector to detect the concentration of the zinc, and it goes to the return valve. If the zinc detector detects that there's still a high amount of zinc concentration, it's going to return valve and send it back to point A, start over the process again. If the zinc detector detects that its concentration is low enough, it's going to get discharged into the oceans or the natural water system. All right, that's all for the purification system. And Then this is a little bit about the economic analysis because to the end, everything comes down to money. So please note that all these costs are estimation. So first we have the conventional method that most oil and gas companies practice nowadays, and the proposed zinc removal method that we have that we proposed. So for the conventional method, it's estimated that shipping fees about $50,000 per platform per month, and labor work is about $30,000 per month. Onshore purifications is about $75,000 per month, and it all adds up to around $155,000 per month. As for our proposed zinc removal method, resins, it costs about $84,000 per year. Equipment is around $50,000, which is a one-time fee to build the whole purification system. And then the maintenance fees is estimated to be around $3,000 per year, and all this adds up to around $164,000 per year. So if to the math, $164,000 per year versus $155,000 per month is definitely going to save quite a lot of money for the oil and gas company. And from the calculation over here, it's going to save about at least $1.7 million per year from this zinc removal method. And in conclusion, and with all the experiments that we did, we can conclude that though X21K and XLT, these resins were effective enough to produce zinc concentrations to below 5 ppm, which excels the EPA requirement. And second, longer incubation time and more cycles of purification is going to improve the removal efficiency of the synthetic and fuel brine. And finally, multi-phase purification system is proposed to provide a longer resin time and larger contact areas. Finally, some recommendation on our projects that need to be further improved. Firstly, the properties such as temperature, pH, and pressure effects are proposed to take into consideration. The reason that we did not do this in our project is because that first, we do not have the proper equipment and environment to do this, and we are actually running on low funding, and we are running out of time to train our project. So, second, more field experiments need to be performed in order to further verify and confirm our lab results. And I guess that's all for my presentation today. Thanks all of you for your time. And if you have any questions, I'll be more than happy to take them.